first question was find the Fourier series representation of this function. Thanks. Okay, good. All right, so I'll just go through. This is sort of how you do it. Basically, the first thing is mainly just plug and chug into the definition for this. The only subtlety I'll comment on and give you a advice or tip on is make sure you find the L, the length, right? That L of the period correctly. Whether it's L or 2L or pi or 2 pi, that's one of the easiest mistake to make. So I will advise you always actually write down what L is. So the first step, actually find the half period. So because in the formulas, they are all defined as from minus L to L. So the repeating part, the periodic part is, so the actual whole period is 2L, right? So L is the half period. Okay, so in this case, what is L? Pi. Good. Yeah. So that's one of the. I know it's trivial if I say it, but when you're in the middle of an exam, it's very. So I'll advise always actually explicitly write it down for yourself. You don't have to write that, but write this down somewhere in the beginning and first line. It just helps you. Okay, and then basically we call the definitions for an and bn. 1 over L minus L to L of x times cosine of kx, 1 over L minus L of L and sine. Okay. And notice that A naught is separately calculated. Do you remember why the A naught is, we need to deal with it separately? Anyone? Even though it looks, sorry, I mean n. Sorry, yeah, n pi x over L. Just to explain my question, right? So A naught, if n equals to 0, it looks almost trivial. Well, cosine 0, it's 1. So why do I need to do this separately and just not do the general L here? The answer is usually when you integrate cosine, usually you get sine, and then this thing has to be divided by the coefficient in front of x. So the n will go to the bottom, right? So if n is 0, if you just do this, you basically, if I just do this, I will get a formula that is correct almost all for all n except for n equals 0. So that has to be done separately. Now you might think, oh, I have a function, so there's some integration by parts. That's true, but even if integration by parts, you will involve a piece where you have to integrate this, right? So eventually you'll get an n on the bottom, right? So that's the reason for this, okay? And I'll call it step 2a. Is before you jump into directly calculating this, the final thing to look at is the function even or odd. That will save you like 10 minutes of work because one of them you don't have to calculate, okay? So let's say check the even or oddness of the function. Right, so since our function inside here is even, therefore this piece will always be 0 for all n. So this immediately saves us half of the work, and we just need to do an and a naught. Okay. So it looks like a straightforward integral. The thing, just glancing ahead in my steps, the only tricky thing over here is to use one of the trigonometry identities. I'll try to skip some of the trivial steps, but you can always slow me down if you need to. Yeah.
Sine function is odd and fx is even. But I thought the product of an even and odd function is an odd function.
That's right. Yes. So if it's an odd function, right? So the whole thing in the integrand, if it's odd, so whatever it's doing on this side is the same as this side. So if you integrate through a symmetric period, it's always going to be 0. Sort of a symmetric domain. Sorry. That's why Bn is 0. Yes. That's by looking at the definition. Another way to think about it is we're trying to write f of x as a series, right? As a naught over 2 plus an plus n pi x over L and ens of sine n pi x over L. So, right, so remember the idea is for most of the time and most of your engineering career, this is probably, so the right hand side is an infinite series, true, but it's going to converge to this when you sum this infinite series. Of course, if you're a pure mathematician, if you do a math degree, you have to worry about does it actually converge to it. So the more rigorous symbol is asymptotically going to that, but you don't have to worry too much. I'm going to be slightly sloppy over here. Yeah. No. So if you just have an integral of some odd function, you're exactly correct that if the range, if you're integrating through a range or a domain that is not symmetric, it won't be zero. Yeah. But of course, the Bn is always symmetric in the definition of in the context of Fourier series. Right. So I was yeah. So another way to look at it is this. Remember, the concept is to approximate a function with the basis instead of, remember, Taylor series is trying to approximate a function, and most of the time, most of the functions that you play with, again, this is going to be equal, right? As we're using the basis being polynomials, right? Instead, in Fourier series, instead of Taylor series, the basis is the sines and cosines, right? An are the coefficients in front of the basis, right? We use the word basis because it's like a vector. If you have a vector, you can write it as a basis like this, right? So it's, you have a basis and then you have a coefficient. So you have a basis like this and these coefficients. Now, if f of x is even, right? If every repeating part is even within the period or half period L, then this captures all the evenness of the function. This captures all the odd part of the function, right? So if I ask you, hey, I have an electrical signal that is doing something like this, right? So it's a triangle, kind of sawtooth kind of wave. So how do you approximate sines and cosines? It's basically you're trying to find some combinations of sines and cosines where if you take that limit, this will actually approximate that very well. So part of this is even and this is a mixture of even and odd. So if you do the Fourier series of this, you will have both an and bn. But if one day you are given a function that is actually even, right? So for example, you need to approximate something like this, just simple, right? Like this. So when you try to do the Fourier series for something like that, you don't expect any odd behavior, no pun intended, into it. So that's another reason why this coefficient should be zero. If your f of x is even, it should not have any odd behavior, right? Or if it's intrinsically odd, it shouldn't have any even behavior in it. Right? So that's more conceptually why you can immediately discard part of the calculation of the coefficient. Right. Okay. A little bit more abstract, but yeah, so just to give you both perspective. Yeah, so the three-step process, right? Find L, write down the definitions, and just apply directly. So A naught isn't really that exciting. So we'll sort of, yeah, there's one quick comment in here that may be useful. Yeah, most of you will know this already. Yeah, so quick integral gives you this. When you plug this in, if this is purely odd, if this is purely an odd function, right, plugging in after you integrate something, it's basically just twice of plugging in the first term. You don't have to plug in the second term. Okay. So what I mean is, we write this out. Sine k pi minus sine k minus pi. because if this is an odd function, I can pull the minus sign out here. So this would just be twice of sine k pi. So it's as if you know this trick or if you've done this many times, this is a step you could mentally skip if you're confident. But if you're not, in an exam, don't risk with your life. Okay, so try to rather you write down the extra step and get the correct answer. But just a quick tip for future reference, right? You can change this to 0 and multiply by 2, and you'll get the same answer. So that's one way to, one thing to keep in mind. Okay, yep. So, and then for this, it's going to be mostly the same, right? So we put in the repeating part of fx times, so that's the fx part, x cosine pi x over L, which is pi. I cancel. So now we integrate cosine kx times cosine nx. Okay, so how do we do this type of integral? So that's maybe the tricky part. That's right, good. So yeah, so there's a series of identity. Let me see if I pull up. It's called the product to sum formulas. Let's see. So for future reference, right? If you in the future, if you are going to do any actual, actual projects in engineering, what you usually do is going to look for product to sum formula. That's what I do, at least. I don't have these. So compound angle formulas, things you learn from A level, those are useful to kind of sometimes depends on how intensive your work is. It might be useful to have them memorized, but no one really memorizes this. So as far as I know, but they exist, but it's important to know that they exist. So what are product to sum formulas are basically taking all 4 possible products, right? Cosine, cosine, sine, 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 cosine, cosine, sine, right? And break them into sum. There's actually a sum to product formula as well, just for future reference as well. And what that does, it takes sums. Yeah, so it takes sums of these and turn it into products. Right? So it's an online exam that you guys are going to do. Technically you can Google that as well, but it's also in your textbook. Either way, yeah, it's fine. Yeah. So right, good. We are going to turn this into a sum. And the reason why we want to turn it into sum is, in general, for integrations, sums are much nicer than products, right? So, differentiation and integration. If I ask you to differentiate, that versus differentiate that, right? Which one's easier? Usually, this one's easier. Same as integration. If I ask you to integrate this, it's very easy. If you ask you to integrate that, basically you first make it like this first, right? So sums are nicer to integrate. All right. So idea is cosine alpha sine beta is, I'll just keep it as A and B for simplicity. It's 1/2 of sine A plus B, right, cosine A plus B, and cosine of A minus B. So it's cosine, sorry, I was quoting the wrong one. Cosine times cosine is basically cosine plus cosine of the sum plus the difference divided by 2. Okay. Right, so we'll apply this 1/2 cosine of k plus n x, right, k plus n, and plus cosine of k minus n. Now it's easy to integrate. I'll pull the 2 out first. So now this becomes So here you can, I'm going to plug this into the x's, and you can use the trick to set this to 0 and multiply by 2, right? With pi. Okay, to simplify this, let's make that one big fraction first and make it k plus n and k minus n on the bottom. So here I have a k plus n, so I need to supplement with a k minus n, sine of k plus n x plus k minus n and sine of, sorry, I have a k minus n, so I need a k plus n and sine of k minus n. Yeah. 1 over pi. Okay, now it's just simplifying this thing. Let's multiply out all the k's. By the way, in the question, you see k is not an integer. Can you see why that is important? I think it should be apparent in this step. Exactly, yeah. So if you have because n is going to, if this is going to go into the series, infinite series, and n is an integer. If k is any integer, right, at some point, this term is going to blow up. Right, so that's the explanation of that. Okay, so now let's group the k's together. Sorry, I should have plugged in the pi already. Right, so I was doing 2 steps at the same time, sorry about that. Plug in the pi over here. The second term, I'm going to plug in the 0, right? So that's going to disappear and multiply extra factor of 2 to compensate for that fact. Right? You can split into 2 steps, but that's one way to do it. Okay. Right, so I have k with this part, k times this part, and then minus n times this part. So minus n times this part, and then plus n times this part. So double negative. The bottom is just k squared minus n squared. This. Okay. Now I have, sorry, I missed the term here, right? It's hard to see on the board. Plus sine of k minus n. All right, that looks slightly better. Apologize for that. Okay, so now I have sine plus sine and sine minus sine. How do we deal with that? Again, this time we look at the sum to product formulas. Okay, so in light of time as well, I'm not going to write those up, but this will recombine. Let me pull out this factor here. Okay. So here I have sine plus sine. It's going to combine into sine times cosine. So the first term becomes 2k. Okay. And then sine to sine, it's going to become 2 times sine of k pi times cosine k pi of n pi, sorry. That is, this part is this plus this. Okay. And then this minus this is n is the same thing, but cosine times sine. 2 cosine k pi. And I don't memorize this, so you like look at the formulas. Which line? Last one or?
First one.
First one
That would be a 2k in the first step.
is 2k. No, this plus this. So the yellow part is k times this plus k times this. So k times this plus k times that.
Oh,
Am I missing some brackets? Probably. Yeah, it's k times this yellow bit and n minus n times this piece. Okay. All right. And then over here, okay, so n is going to be an integer. This term over here will always be 0. If you look at a unit circle, right? Sine of n pi will always be 0. So we just have the yellow piece over there. So we have 2k over pi. I'm just pulling the 2k in front. K squared minus n squared. Sine of k pi times cosine of n pi. Let's directly write it as minus 1 to the power of n. Okay, so just to get it simpler. Okay. And that's almost it. We just need to put it into the Fourier series. The last step is to put it in the Fourier series. And that's it. To be frank, to be honest, in the multiple choice questions, the Fourier series and Fourier transform is probably going to be the one that you spend the most time on. You're not going to evenly distribute all the times between eigenvalues and things like that. So the eigenvalues question, some of the easier ones, you should expect to get through them around 5 minutes per question. So you have 4 hours for the whole thing. I would at least spend. So technically, the original exam, if it's in person, is 2 hours. So I would allocate, if it's a 2-hour exam, I'll allocate 1 hour for the section B. Right? 1 hour for section A. So some of the easy ones spend 5 minutes or so. These ones, at least 10 to 15 minutes, it's normal. Okay, so there are few of them you would be per them, but now you have a 4-hour window. It's a little bit more relaxed with that. Sorry. Oh, it's separately. Oh, okay, yeah, all right. Okay, yeah, so now you put everything together. So A naught is that, so you have 1 over, remember it's A naught divided by 2. I think I erased the thing somewhere, but yeah, so it's A naught divided by 2, so yeah, let's write it. And cosine so that divided by 2, 1 over pi k of sine a pi plus that 2k over pi 1 over k squared minus n squared times sine of k pi minus 1 to the power of n. Remember to multiply the cosine of n pi x over L, but L is pi, so and x as well, and no bx term. Okay,